In the last lecture, we discussed hierarchical clustering, where observations are sequentially grouped to create clusters. A useful graphic display for hierarchical clustering is called dendrogram, which is a tree-like diagram that summarizes the process of clustering. In hierarchical clustering, we often use the dendrogram to determine the number of clusters. The fact that we do not have to specify the number of clusters beforehand is appealing because cluster analysis is an unsupervised data mining technique. Therefore, it is impossible to know for sure how many clusters we have beforehand. In addition, the dendrogram can clearly show how data are clustered. But when you have too many observations, the dendrogram can get overly complicated and becomes less useful. Therefore, hierarchical clustering is best suited for situations where there are a relatively small number of observations in the dataset. Hierarchical clustering is quite computationally intensive, as it requires the computation of the distances between all possible pairs of observations. For example, if we have a small dataset with only 100 observations, hierarchical clustering will need to create a 100 by 100 distance matrix and compute the distances between 4,950 possible observation pairs. The number would increase exponentially if the dataset is much larger. Another limitation of hierarchical clustering is low stability of the cluster structure. First, the algorithm only makes one pass through the data to assign observations to clusters. Second, different choices of distance between clusters, such as single, complete, or average linkage, tend to lead to very different cluster structures. And dropping or modifying observations can also lead to very different cluster structures. In addition to the hierarchical clustering solution, there is also the non-hierarchical clustering approach that does not share some of the problems that hierarchical clustering has. The non-hierarchical clustering approach, also called k-means clustering, is the most popular algorithm used in cluster analysis. The technique pre-specifies a desired number of non-overlapping clusters, or k-clusters, and assigns each observation into a cluster so that each cluster is as homogeneous as possible. Compared to hierarchical clustering, k-means clustering algorithm is more computationally efficient and only requires the computation of the distances between each observations and the k-cluster centers. For example, in the same 100 observation dataset that we mentioned earlier, if we want to group the observations into 4 clusters, k-means clustering will only need to compute the distances between the 100 observations and 4 cluster centers, or 400 distance measures, during each iteration. Furthermore, due to the iterative process employed in k-means clustering, the resulting cluster structure is usually more stable and less likely to be affected by small changes to the dataset. So the basic idea of k-means clustering includes the following 2 key points. First, it divides the dataset into a predetermined number of clusters, so that each cluster is as homogeneous as possible with respect to the chosen variables. The algorithm does this by minimizing the average distance between each observation and the cluster center of the cluster it belongs to, in order to create stable and well-formed clusters. Since the distance is usually measured using the Euclidean distance, K-means clustering is designed to work with observations with numeric variables. However, in some cases, categorical variables can be converted into numeric variables through dummy variables or category scores. But the performance of such approach is often questionable. Other techniques, such as the k-modes clustering, which uses the modes instead of means to find cluster centers, have been proposed for dealing with categorical variables, or using the principal components as inputs for cluster analysis if you are dealing with mixed data. Those techniques are beyond the scope of this class, so we won't discuss them in this lecture. In this lecture, we focus on performing k-means clustering on numeric variables, which is the most common use of this technique. As in hierarchical clustering, the clusters in k-means clustering are formed based on the input variables you select. Therefore, the selection of the input variables plays an important role in determining the cluster structure. If inappropriate input variables are selected for the problem, the cluster structure generated would not be meaningful and can even be misleading in some cases. Domain expertise is especially important in unsupervised data mining problems such as clustering, because there is no validation available to check your results. Therefore, these analyses need to be driven by sound business understanding instead of just the data. While the input variables you select for clustering will differ based on the business questions, there are some general guidelines about the input variables you should choose. First and foremost, these variables need to be meaningful to the analysis objective. You should identify variables that provide useful information about the segments you are interested in. Since you don't have a target variable in clustering, relevance of the inputs is determined based on your domain knowledge. Eliminate any variables that do not clearly have anything to do with your desired segments. For example, if the goal of your cluster analysis is to identify groups of customers to target for products at different price points, then input variables related to income, spending patterns, and price sensitivity may be good candidates. Second, the input variables should be relatively independent. The reason is that distance measures such as Euclidean distance do not account for the interactions between variables. Therefore, it is recommended that variables that are highly dependent on each other be combined into one variable or reduced to only one representative variable, instead of including all the variables. Third, there should be only a relatively small number of key input variables. The analyst should be selective about which variables to include in the analysis. If too many variables are included, it increases the risk of including variables that are less relevant to the business objective, and your data may suffer from the curse of dimensionality. The curse of dimensionality means that as the dimensionality of a dataset increases, a fixed number of observations become increasingly sparse in this high-dimensional space. When these observations are very far apart, it is difficult to come up with meaningful clusters to group the observations. Fourth, it is recommended that the variables have a measurement level of interval. In other words, are all numeric. This makes the dataset more readily usable when the Euclidean distance measure is applied. Finally, the variables should have low kurtosis and skewness. This is because that cluster analysis results are significantly impacted by outliers. However, in certain applications of cluster analysis, such as fraud detection, identifying outliers that do not belong to any clusters is actually the goal of the analysis. So not all outliers should be removed prior to the analysis. As you can see from the discussion here, cluster analysis is more art than science. The key difference between hierarchical and k-means clustering is the pre-specification of the value of k. In k-means clustering, you need to specify the number of resulting clusters prior to the analysis. So how do you know how many clusters will emerge from the dataset before you even perform the analysis? Well, there are a number of sources for the value of k, including prior knowledge, practical constraints, experimentation, and the software recommendation. Let's discuss this important topic. As I mentioned earlier, domain expertise is critical in cluster analysis. Subject area experts may have some prior knowledge that can help us identify the appropriate number of clusters even before the analysis. For example, an experienced marketing manager who has spent decades dealing with customers may know in his or her heart how many different types of customers that the company has. In this case, we are informed by prior knowledge to find the appropriate value for k. Sometimes there are practical constraints that dictate the number of clusters we need to find. For example, a firm is trying to market 3 different products with high, medium, and low price points and different sets of functionalities. Then it makes sense to divide potential customers into 3 groups or clusters, hoping that each cluster would contain customers to target for each of the products. In this case, the practical constraints provide a reasonable starting point for identifying the value of k. When it is difficult to know which value of k to choose, one can also experiment with different values of k and review the resulting cluster structures to see which cluster structure makes the most sense or best serves the objective. Finally, one can also solicit software recommendation for the optimal value for k. This feature is often available in many data mining software products, including SAS Enterprise Miner. One popular technique for the software to make a recommendation without understanding the underlying meaning of the data is called Watts method, which I will explain in the next couple of slides. In a nutshell, Watts method is a hierarchical clustering technique which sequentially groups the observations into clusters. During every clustering step, it considers the loss of information that occurs when observations are clustered together. The loss of information is quantified using a measure called error sum of squares, or ESS. The ESS is computed as the sum of the squared differences between an observation and the cluster centroid. The idea is that clustering is the process of generalization. When observations are grouped into clusters, they lose their individual identity, and instead are represented by the cluster identity, which is often manifested by the cluster centroid, or cluster center. When that happens, you lose the information about individual observations. ESS quantifies how much information is lost on the individual observations by generalizing these observations in the same cluster using the cluster centroids. To better illustrate this idea, let's look at a very simple example. Let's say we have the 5 observations in the slide, and each observation has only one input variable. The value of the input variable for the first observation is 3, 5 for the second observation, 8, 15, and 16 for the third, fourth, and fifth, respectively. You can imagine these observations as customers, an input variable to be anything, such as income, age, length of being a customer, annual spending, and etc. Our goal is to cluster these observations into clusters that are relatively homogeneous within each cluster. The question is, how many clusters would make sense? In the next slide, let's see how the Watts method helps answer the question. As mentioned earlier, the Watts method is essentially a hierarchical clustering technique, more specifically, an agglomerative hierarchical clustering technique. So it starts with every observation as its own cluster, as shown in the first row here. If each observation is its own cluster, then no information about individual observations is lost because the cluster is the individual observation. We can compute the error sum of squares, or ESS, by summing up the squared differences between the observations and cluster centers, which are the observations in this case. So as you can see, the ESS turns out to be 0, indicating that no information is lost at this stage. As we can intuitively see, the 4th and the 5th observations are the closest to each other because of the difference between the two observations is only 1. So we first cluster observations 4 and 5 together. When these two observations are clustered together, the cluster centroid would be the average of observation 4 and 5, which is 15.5. If we compute the ESS for this cluster structure with 4 clusters, the ESS turns out to be 0.5, which suggests some loss of information. Next, we cluster observations 1 and 2 together because they are closest to each other. Then the ESS becomes 2.5, indicating further loss of information. One thing you will notice is that when we went from 5 clusters to 4 clusters and then to 3 clusters, the ESS value increased slightly from 0 to 0.5 and then to 2.5. This suggests that clustering did not result in significant loss of information. This is an indication that the sequential clustering process should continue to form well-structured clusters. As we cluster observations 1, 2, and 3 together in the next step, we notice that the ESS value had a relatively large jump from 2.5 to 13.167. However, such loss of information may still be tolerable, as going from 3 clusters to 2 clusters represented about 5-fold increase in information loss, which is about the same as the percentage of information loss when we went from 4 clusters to 3 clusters. when we try to cluster all 5 observations into one large cluster in the last iteration. The ESS jumped to 134.6, which is a much severe loss of information. Usually when the loss of information increases dramatically like this, that is when we know that we have gone too far in terms of clustering the observations. In this case, it suggests that the 2-cluster structure makes sense because it represents the most reasonable balance between the need to cluster and the amount of information loss that is tolerable. Therefore, we would suggest the use of k equal to 2 for performing k-means clustering for this example. As you can see from this demonstration, how we know the amount of information loss is too much is quite subjective. Software packages usually would convert the ESS measures into a percentage measure, for example, R², which equals to the difference between the total sum of squares and error sum of squares, and then divided by the total sum of squares. That can be compared to a threshold value to determine the optimal k to recommend. Now that we understand how k can be determined, let's take a look at the k-means clustering algorithm to understand the process. The process is quite straightforward and can be summarized into these 6 steps. Step 1. We select the input variables by identifying the relevant variables for the business objective. Step 2. We select the value of k and randomly assign k cluster centers for the dataset. In some cases, the algorithm would randomly select k observations from the dataset to act as the cluster centers during the first iteration. Step 3. The algorithm assigns the cases to their closest cluster centers using Euclidean distances. Step 4. Once all cases have been assigned to their initial clusters, the algorithm updates the cluster centers by calculating the cluster centroids for the k clusters. Step 5. With the cluster centroids as the updated cluster centers, the algorithm now reassigns the observations to their closest cluster centers, thus changing the cluster structure. Step 6. The algorithm will repeat step 4 and 5 until convergence, which means that the cluster structure reaches a stable state and would no longer change. In some cases, convergence comes after a few iterations, and in other cases, it may come after many iterations to reach convergence. Now let's take a look at a visual enactment of the k-means clustering process. In this example, we have selected 2 variables, x1 and x2, and they can be any numeric variables that are relevant to the business objective. By plotting the observations along the 2 axes, we have the visual representation of the observations in the slide. Remember, like other demonstrations in this course, this applies to situations where there are more than 2 dimensions. It is simply difficult to show them visually. Therefore, we choose to only show the example with 2 dimensions, but the concept can be extended to higher dimensional situations. Suppose we decide to create 5 clusters. Therefore, k equal to 5. We select 5 random cluster centers. These cluster centers can be 5 randomly selected observations in the dataset, or just 5 randomly selected points in the space. Please note that one limitation of k-means clustering is that different initial starting points can lead to different resulting cluster structures. Therefore, sometimes it is recommended that k-means clustering be performed multiple times using different initial starting points, and then pick the most meaningful cluster structure as the final result. Now the algorithm computes the Euclidean distances between each observation and each cluster center, and then assigns the observations to their closest cluster centers. As you can see, 5 clusters were formed, shown in 5 different colors. Please pay closer attention to the yellow cluster. It seems to be the smallest cluster of all, with only a few observations. And the current cluster center is to the right of all the observations that belong to the yellow cluster. In the next step, the algorithm updates the cluster centers by recalculating the cluster centroids using the observations in the clusters. Let's see what happens to the yellow cluster. As you can see here, the cluster center of the yellow cluster has moved to the left. The cluster centers of other clusters also moved, but not as dramatically as the case of the yellow cluster. Now the cluster centers are more physically located in the middle of the clusters. We now reassign the cases based on the new cluster centers. As you can see, the yellow cluster got a little larger and includes more observations now, because there are more observations that are closest to the updated cluster center for the yellow cluster now. Other clusters also got adjusted. You may want to replay this and the previous slide again to see how the clusters changed. What we have seen so far is the first iteration of k-means clustering. The iteration will continue in the next few slides. We now repeat steps 4 and 5 to update cluster centers based on the new cluster structure, and reassign cases to clusters based on their distances to the updated cluster centers. As you can see in this case, the yellow cluster got even larger now. We now go through another iteration of updating cluster centers and reassigning cases. Then another iteration. As you can see, the yellow cluster got even bigger. Another iteration here, and another iteration. And finally, we reach convergence, when the cluster centers or the cluster structure will no longer change. So this demonstration shows you visually how k-means clustering is done. If you feel that I went a little too fast, please feel free to go back and watch the demonstration again so that you understand the algorithm. To summarize, k-means clustering requires that we pre-specify the number of clusters k prior to the analysis. Starting from the randomly selected k cluster centers, the algorithm takes an iterative approach to assign the observations to their nearest cluster centers and update cluster centers until the cluster structure no longer changes. While k-means clustering is the most popular clustering technique, you should understand its key limitations. First, as we discussed, finding the appropriate k value can be difficult sometimes. Second, k-means clustering is designed to work with numeric data only. Other data types will require pre-processing before k-means clustering can be applied. As k-means clustering uses Euclidean distance measures, standardization or normalization is needed to remove the impact of the measurement scales. In k-means clustering, the resulting cluster structure may be influenced by the choice of the starting cluster centers. Therefore, it is recommended to try a few different starting cluster centers to identify the cluster structure that makes the most sense. K-means clustering is impacted by outliers. Outliers can drag the cluster centroid toward them, so it is recommended that outliers be removed prior to the analysis. Finally, k-means clustering assumes that we are dealing with spherical clusters, and that each cluster has roughly equal number of observations. This assumption allows the algorithm to result in more evenly distributed clusters. However, in some cases where this assumption is not satisfied, this can make k-means clustering less effective. For example, in anomaly detection or fraud detection, the number of cases that are anomaly or frauds is usually relatively small. Then k-means clustering can be less effective in identifying the right cluster of anomalies. Now that you understand the concept of k-means clustering, let's look at how to solve a problem with k-means clustering. In this scenario, Aaliyah Williams is trying to group candy bars into meaningful clusters in order to improve product selection and display for her vending machines. Let's cluster the candy bars in the dataset into 4 clusters using the k-means clustering technique.